now that we have defined directional derivatives, we can get a better understanding of the interpretation of the gradient vector. So the theorem says, suppose that f of r is a differentiable function, then the maximum value of the directional derivative is the magnitude of the gradient. And it occurs when u has the same direction as the gradient vector grad f of r. So what this is saying is that the gradient tells us the direction of greatest increase. And that is the interpretation that we can use when thinking about the gradient vector. So why would this be true? Well, suppose that you're looking at the directional derivative in the u direction of f of r. We have just shown that this is the gradient of f of r dotted with u. Okay? One way that we can compute a dot product is we can say that this is the magnitude of the first vector, which is the gradient, times the magnitude of u times cosine of the angle theta between those two. Now, u is a unit vector, so that has magnitude 1. And then the cosine of theta we know is between -1 and 1. So in fact, if we want to look at the magnitude of the directional derivative, that's equal to the magnitude of the dot product of the gradient with u. Okay, that's equal to the magnitude of the gradient of f times the magnitude of u times the magnitude of cosine theta. The magnitude of cosine theta is less than or equal to 1, so this whole thing is less than or equal to the gradient of f. So this says that the maximum value of the directional derivative is the gradient. Now the next question though is, when is this maximum achieved? Okay, so the maximum is going to be achieved when cosine of theta is equal to 1. So for what angle is cosine of theta equal to 1? That's when theta is equal to 0. And so if the gradient is in the same direction as u, the directional derivative is maximized. Okay, so what we're saying is for the function f of r, the direction of greatest increase is going to be the gradient of f, and the direction of greatest decrease is actually going to be in the opposite direction. It's going to be minus the gradient of f, because we can also say that the minimum is achieved when cosine of theta is equal to -1, or that's when theta is equal to pi. So it's in the opposite direction. So the gradient is going to tell us that direction of greatest increase, or minus the gradient tells us that direction of greatest decrease. Okay, and the magnitude of the gradient, that's going to tell us the maximum value of the directional derivative. Well, this has some practical uses. So let's look at an example. This example says that the concentration of a chemoattractant MCP1 is given by f of x, y, z equals e to the minus x squared minus y squared minus z squared. Okay, a chemoattractant is a chemical signal that attracts immune cells in your body. So if you have some sort of infection, then the immune cells need to know where to go, and so they're attracted by something like this chemoattractant MCP1. Okay, so how would the immune cells know where to go? Well, maybe they need to find the direction of greatest increase. Okay, so here we're going to find the direction of greatest increase of F at the point 1, 0, 2. Okay, so here, the gradient of F, okay, the gradient of F is going to be, let's take the derivative. So the derivative of e to the minus x squared minus y squared minus z squared is itself. So it's always going to be itself. So I'm going to put this on the outside of the vector. So it's itself times the derivative of minus x squared minus y squared minus z squared. That's minus 2x. The y derivative of that exponential is itself times the derivative of the inside, which is minus 2y. And then the z derivative is also itself times the derivative of the inside, which is minus 2z. So we might write this, if we like, as minus 2 times the vector x, y, z times the exponential e to the minus x squared minus y squared minus z squared. So it's interesting to point out, in this case, that the direction of the gradient, okay, if I want to make that, say, a unit vector, the direction is going to be minus x, y, z divided by the magnitude, which is the square root of x squared plus y squared plus z squared. So if you found the magnitude of the gradient of f, and then you divided the gradient of f by its magnitude, you would get this vector. And that's interesting because it points towards the origin. So in this sense, it's pointing towards the center of this function, e to the minus x squared minus y squared minus z squared. So it's pointing it towards 0, 0, 0. That is, of course, where this function is the largest, right? E to the minus x squared minus y squared minus z squared, that's going to be maximized when x, y, and z equals 0, so that the exponential is e to the 0, which gives you 1. If x, y, or z is positive or negative, if it's non-zero, then you're going to get e to the minus a positive number. That's going to be smaller than e to the 0. Okay, so the direction that this gradient vector is pointing in is toward the center, okay, towards 0, 0, 0. That's where the function is the largest, okay? If we want to look at the point 1, 0, 2, okay, then the gradient of f in this case is going to be negative the gradient of f in this case is going to be negative 2 times 1, 0, 2. Okay, and that's an e to the minus 1 squared plus 0 squared, or minus 0 squared minus 2 squared. So this is going to be e to the minus 5. Okay, so the magnitude of the gradient, okay, is going to be the magnitude of this, okay. That's going to be 2e to the minus 5 times the square root of 5. Okay, and so the magnitude of the gradient there gives you, it gives you the rate of increase at the point 1, 0, 2. Okay. Another thing that I asked for was the direction of greatest increase. Okay, so the direction of greatest increase at that point is going to be negative 1, 0, 2 divided by the square root of 5. So this is going to be the direction, and this is going to be the magnitude. Okay, so what's really going on here? Well, we have this function, e to the minus x squared minus y squared minus z squared. That's giving the concentration of this chemoattractant. And what happens is that an immune cell in your body, okay, it's going to be sitting in that concentration of the chemoattractant, and it's going to have little sensors on it. So it's got sensors that go around its surface here. And what will happen is it's going to note that the concentration on this side of the cell, okay, is larger than it is on the other side. And so the cell actually is going to use that information to compute a gradient, and that gradient is going to point it in the direction of the source of this chemoattractant. And that source of the chemoattractant is likely going to be some sort of an infection. And so what you have here is you have gradient sensing cells in your body. Okay, your immune system has gradient and sensing cells. They are looking for the direction of greatest increase of the concentration of that particular chemical so that they know which direction to go to fight that infection. And so essentially, your cells in your body are doing multivariable calculus all the time to be looking for those infections. Okay. And now I want to look at another interpretation of the gradient that we're going to be able to get. And that is, suppose that f of r has continuous partial derivatives, and r0 be a point on the level set f of r equals k. So in other words, f of r0 is equal to some constant. And at this point, the gradient is not allowed to be 0. The gradient of f of r0 is not 0. If r of t is a differentiable curve on the level set f of r equals k, with r of t0 equal to r0, and then the derivative of that curve is not 0, then what can we say? We can say that the gradient of f at r0 dotted with r prime of t0 is equal to 0. Okay, so if the dot product of two vectors is 0, what that means is those two vectors are perpendicular. And so we're saying that the gradient is going to be perpendicular to r prime of 0, r prime of t0, but r prime of t0 is the direction of the tangent vector. Okay, so the gradient is going to be perpendicular to the tangent vector for the level set f of r equals k. So therefore, it's actually going to be perpendicular to the level set f of r equals k. Now, this is best illustrated by looking at some pictures in 2 and 3 dimensions. Okay, so what I'm going to do is I'm going to draw some level curves. Okay, so I'm going to let f of xy equal k be a level curve of the function. So I'm going to draw some level curves here. So here along these blue curves, we're going to get that the gradient is, that along these level curves, we're going to get that the function is constant. So along each of these blue curves, our function is constant. So we could say, like here, f is equal to k1 on that curve, f is equal to some number k2, f is equal to some number k3, here f is equal to some number k4. So along each of those curves, okay, my function is constant. And now what I'm saying is that if I pick a point that point is going to be R0 or R of t0. So if I pick that point R0, then the gradient is going to be perpendicular to the level curve. So the gradient of f at R0 is going to be perpendicular to R0. Okay? What do I mean by perpendicular? What I mean is that if I look at the tangent to the curve, the gradient is perpendicular to that tangent. So this would be R prime of t0. So the gradient of my function f is always going to be perpendicular to those level curves. Okay? So what we've done is we've parameterized the curve, that level curve, so f of r of t, that's like saying f of x of t, y of t is equal to k. And then what we're saying is that the gradient of f of x of t, y of t, dotted with the derivative of x of t, y of t, so x prime of t, y prime of t, we're saying that that dot product is going to be 0. Okay, that's what shows that the gradient is perpendicular to the level curve. Okay, so in fact, actually, we're going to put t0 here because we picked a specific point. Okay, so the gradient is always going to be perpendicular to those level curves. Okay, that's in 2 dimensions. Okay, what about if we go to 3 dimensions? Okay, so in 3 dimensions, we have level surfaces. Okay, so what we're going to say is that there's a bunch of these surfaces. So maybe there's a surface like this. Okay, and on that surface, okay, my function is constant. Okay, so maybe there's a bigger surface. Okay, and on that surface, okay, my function is constant. Okay, along these different surfaces, my function is constant. So here we're going to say on this surface that f is equal to k. Well, then what we're going to say is that if you have the gradient from this surface, okay, the gradient is going to point perpendicular to that entire surface. Now, why is it going to be perpendicular to the entire surface? Because what we said is that the gradient would be perpendicular to a curve. Okay, so in fact, it will be perpendicular to a curve because we can just put a curve on the surface. Okay, and that gradient is going to be perpendicular to that curve. Or we can put another curve on the surface, okay, and then the gradient is going to be perpendicular to that curve. So the gradient is going to be perpendicular to any curve that lies on that level surface. So it's going to be perpendicular to the entire level surface, okay? And so if it's perpendicular to the entire level surface, okay, it turns out that it's going to be perpendicular, okay, to the tangent plane to that surface. So if we drew a tangent plane at that point, okay, the gradient is going to be perpendicular to the tangent plane to that surface. Okay, so what we're learning here for this level surface is that the gradient of f is perpendicular to the surface. So we say that it's normal to the surface, f of, let's say, x0, y0, z0 equals k. Okay, so it's perpendicular to that surface. Actually, I'm going to write it as f of x, y, z equals k at x0, y0, z0. So that means it's perpendicular to that tangent plane. So that means that the gradient of f at x0, y0, z0, if we dot that with x minus x0, y minus y0, and z minus z0, then we're going to get 0. Okay? That's coming from the fact that the gradient is perpendicular to that surface. And so that is the equation of the tangent plane. Okay, so we have a level surface. The gradient is going to be normal to that level surface. So now if we want to find a equation of a tangent plane to a surface, and an implicit surface, okay, then we can do that using the gradient. Okay, so this is it's the equation of the tangent plane to that level, or you could even say it's an implicitly defined surface. Okay, so this is the picture of what it looks like in 3 dimensions. Okay, gradients are perpendicular to level curves. Okay, they're normal or perpendicular to level surfaces. Okay, now I've stated this, but why is this true? Why is it that the gradient is going to be perpendicular to a level surface? Well, this is actually not too hard to see. Okay, so we're going to let f of r of t equal k. Okay, that's going to be a level curve or surface. Okay, so that's a differential or differentiable curve on our level set. Okay, then if I take the derivative of both sides, I get the derivative of f of r of t equals the derivative of that constant k. Okay, on the left side, we have the chain rule. And by the chain rule, we have that the gradient of f of r of t dotted with r prime of t, okay, is equal to 0. Okay, so by the chain rule, the gradient dot r prime, that's the left side, is equal to the derivative of k, and that derivative is going to be 0. So at t equals t0, we're going to get that the gradient of f of r of t0 dotted with r prime of t0 is 0. That shows that the gradient is perpendicular to the level curve at t equals t0. Okay, so the chain rule here is essentially what's going to be telling us that the gradient is perpendicular to these level curves. And that's a cool result there. Okay? So, in fact, if you think about it, this expression, okay, of the chain rule, the gradient dot r prime, okay, that's really a directional derivative. We're looking at the derivative of f in the direction of r. Now, it's not quite the directional derivative because we haven't used the magnitude here, okay? But this is an expression that's giving us kind of the directional derivative. Okay. let's look at two examples to finish up. Okay, the first example says, find a unit vector that's normal to the surface S, which is given by z equals x squared y squared plus y plus 1 at the point 0, 0, 1. Okay, so we want to find that normal vector, okay, to the surface. So what we're going to do is we're going to define the surface f of x, y, z, and that's going to be x squared y squared plus y minus z. I'm going to bring the z over to the other side there. Okay, plus 1 equals 0. Okay, and this is going to be a level surface then, because I've set it equal to 0. Okay, by setting everything equal to 0, I have a level surface of capital F. Or sorry, of just F. Okay, now if I want to find the normal vector, so then I'm going to find the gradient of F. The gradient of F in this case is going to be, the derivative with respect to x should be 2xy squared. Everything else doesn't have an x in it. The derivative with respect to y should be 2x squared y plus 1. Nothing else has a y in it. And then the derivative with respect to z should be negative 1 because negative z is the only term that has z in it. The gradient of f, if I specifically put in the point 0, 0, 1, okay, that's going to give us 0, 1, negative 1. Okay, so this is a vector that's perpendicular to the surface. So the gradient of f divided by its magnitude in this case is going to be 0, 1, negative 1 divided by the magnitude of that vector, which is the square root of 2. And so now I found a unit vector that is perpendicular, okay, to that surface. Let's look at a second example. Let's compute the tangent plane to the surface defined by 3xy plus z squared equals 4. So this is already implicitly defined, and then we want to do that at the point 1, 1, 1. Okay, so that's our function. F of x, y, z is going to be 3xy plus z squared, and then we set that equal to 4 so that it'll be a level surface. Okay, the gradient of f in this case is going to be, the derivative of 3xy is 3y when I take the derivative with respect to x. If I take the derivative of 3xy with respect to y, I get 3x. And then the derivative of that first part with respect to z is 0, and then the derivative of z squared is 2z. So the gradient of f at 1, 1, 1 is equal to 3, 3, 2. So that gives me the normal vector. And now if I want to look for the tangent plane, okay, I have my normal vector. It's going to be 3, 3, 2. And then I'm going to dot that with x minus x0, y minus y0, and z minus z0. Okay, so that's my point here, x0, y0, z0. And that dot product is equal to 0. So this says 3 times x minus 1 plus 3 times y minus 1 plus 3 times z minus 1 is equal to 0. Or 3x plus 3y plus 3, sorry, that is a 2 times z minus 1 plus 2z is going to equal, well, I've got a negative 3, a negative 3, and a negative 2, and they all add up to 8 when I bring them to the other side. And so that's my equation of my tangent plane. And so what I encourage you to do is to plot this implicit surface in something like CalcPlot 3D, and then plot the tangent plane, and you should be able to see that the plane is in fact tangent.